Welcome to the lecture on elimination reactions. Elimination reactions are organic reactions in which a pair of atoms or groups are eliminated from a molecule by the action of acids, bases, metals, or by heat. Here I have given an example of an alkyl halide undergoing elimination by the action of a base. Halogen is connected to a carbon, and that carbon is called alpha carbon. The next carbon is called beta carbon. So halogen from alpha carbon, hydrogen from beta carbon are eliminated by the base, resulting in the formation of an alkene. Based on the positions of the leaving groups, the elimination reactions are classified as alpha elimination, beta elimination, or 1, 3 or 1, n eliminations. But most of the elimination reactions are beta eliminations, which are called 1, 2 elimination, in which the leaving group from alpha carbon of the substrate and a proton from the beta carbon are eliminated as given here. So this is an example for alpha elimination. Two groups X and Y are eliminated from the same atom. This is called alpha elimination. In this reaction, the leaving group X is present in alpha carbon, the group Y is in beta. X and Y are removed from alpha and beta carbon atoms. Therefore, this is called alpha comma beta elimination, but we don't call it as alpha comma beta elimination. Usually, we call it as beta elimination or 1, 2 elimination. And this beta elimination always results in the formation of an alkene. And this is an example for 1, 4 elimination. A group in carbon 1, this is 2, 3, 4. A group in carbon 1 and 4 are eliminated, and this results in the formation of a diene, and this is called 1, 4 elimination. Here are few examples given for elimination reactions. This is an example for alpha elimination. Alpha eliminations are those in which two geminal groups. Geminal groups are the groups connected to the same carbon atom. Two geminal groups are eliminated to generate carbenes. Carbene is an unstable divalent species which is useful for many other reactions. So this is dichlorocarbene. Chloroform, when treated with sodium hydroxide, hydroxide base removes the acidic hydrogen, resulting in the formation of dichloromethyl carbanion. From that, chloride ion is eliminated to generate a dichlorocarbene. So this is an example for alpha elimination. And here is an example for 1, 2 or alpha, beta elimination, or simply we call it as beta elimination. A leaving group halogen is connected to this carbon. This carbon is called alpha carbon, and the next carbon is beta, and the beta carbon has a hydrogen that is called beta hydrogen. When we add a strong base like alkoxide, it removes a proton from here, from the beta carbon, and a halide or the leaving group from alpha carbon. So two groups are eliminated from alpha and beta carbon atoms, resulting in the formation of an alkene, a olefin. More about the mechanism of this kind of reactions we are going to discuss later. Here is another example for 1,4 elimination. Two halogen atoms are eliminated when we heat it with zinc. So this is 1,4 elimination. So alpha elimination, beta elimination, 1,4 elimination. So these are few examples. Let us look at a few more examples for alpha eliminations. Elimination of hydrogen chloride from chloroform using a base. This is the reaction we discussed just now. Another reaction is an elimination from Zimmermann rearrangement, resulting in the formation of a methylene. Halogen and the zinc iodide part from this side are eliminated from the same carbon, resulting in the formation of a carbene, CH2, methylene. Another elimination is elimination alpha. Another alpha elimination is elimination of nitrogen from alpha diazoketone by using light. This is called Wolff rearrangement. So alpha diazoketone, this is diazo, this is carbonyl ketone. With respect to carbonyl group, this is alpha. Therefore, this is called diazoketone. So diazoketone on exposure to light undergoes a rearrangement like this, and it results in the formation of a ketene as the product. So from the same carbon, these two bonds are removed. A nitrogen molecule is eliminated. So this is also an example for alpha elimination. Curtius rearrangement is another example for alpha elimination. Here is an acyl azide. An acyl azide undergoes rearrangement like this, and on heating it loses this part of the molecule. These two bonds are removed. A nitrogen molecule is removed from here, resulting in the formation of an alkyl isocyanate. So acyl azide on heating loses a molecule of nitrogen. These two bonds are eliminated, resulting in the formation of isocyanate, from which we can prepare. This is a good intermediate for the preparation of various products like carbamates. By treating with alcohol, by treating with water, we get amine, and then by treating with an amine, we get urea derivative. So that way, this alpha elimination, Curtius rearrangement, is useful in the preparation of various products. In alpha eliminations, two groups were eliminated from the same carbon atom. Two groups connected to the same carbon atom are called geminal groups. So two geminal groups were eliminated in alpha eliminations. But in beta elimination or alpha comma beta elimination, two groups are eliminated from vicinal carbon atoms. Two vicinal groups are eliminated. Two groups are eliminated from adjacent carbon atoms. So the groups connected to the adjacent carbon atoms are called vicinal groups. So in a beta elimination, two groups present in the adjacent carbon atoms are eliminated. The common organic substrates which undergo beta elimination are alkyl halides, alcohols, and even quaternary ammonium salts. Here I have given an example for dehydrohalogenation of alkyl halide. Alkyl halides on treatment with a base undergo dehydrohalogenation resulting in the formation of an alkene. The carbon to which halogen is connected is called alpha carbon. The next carbon is called beta carbon, and the hydrogens present here are called beta hydrogen atoms. So with this alkyl halide, when we add a hydroxide base, it abstracts or removes a proton from beta carbon. A H plus from beta carbon is removed, and then the resulting minus charge will make a bond here and will push the halide out. So a H plus from beta carbon, halide from alpha carbon are eliminated to form an alkene. The detailed mechanism of the beta eliminations we will be discussing later. Here I have given another example for beta elimination, that is dehydration of alcohols. When an alcohol is treated with a strong acid like concentrated sulfuric acid or concentrated orthophosphoric acid, the OH group will get protonated and will become a good leaving group, and it will be removed as water molecule, resulting in the formation of a carbocation. So the fate of carbocation is either joining with an anion or undergoing deprotonation. So here, once carbocation is formed in the alpha carbon, a proton or a H plus is removed from the beta carbon. Deprotonation takes place, and that results in the formation of an alkene. Hoffman elimination is another example for beta elimination, and this is an elimination reaction, beta elimination reaction taking place in a quaternary ammonium salt by heating with a base. The quaternary ammonium salt has a nitrogen connected to a carbon. This is alpha carbon, and the next carbon is beta carbon. The beta carbon should have at least one hydrogen here. Only then beta eliminations are possible. So when we heat this quaternary ammonium salt with a base removes a proton from beta carbon. The resulting negative charge makes a double bond here, pushing the tertiary amine out, resulting in the formation of an alkene. So in the reactant molecule, in the substrate, all the carbon atoms are sp3 hybridized with bond angles of 109 degrees 28 minutes. But the product is a olefine, where we have sp2 hybridized carbon atoms with bond angle of 120 degrees. So the bond angle increases after the elimination. Therefore we can say there is removal of angular strain. So the bond angle from 109 degrees 28 minutes becomes 120 degree here. So there is some relief from angular strain. So the two factors which are leading to successful elimination reactions of this type are the stability of the unsaturated product generated, normally alkene. Number two is the extent to which there is removal of angular strain or steric strain taking place. Beta eliminations are more readily taking place in tertiary substrates than the secondary and primary. This is the order in which the elimination reactions are taking place. The fastest elimination is with tertiary substrates. So here I have given an example for a tertiary substrate. Halogen, the leaving group, is connected to a tertiary carbon. This carbon is connected to three alkyl groups. So this is a tertiary substrate. When it is treated with a base, it undergoes dehydrohalogenation to form an alkene. So in this carbon, there are three bulky alkyl groups which are causing more steric strain. So the angle between any two alkyl groups is 109 degrees 28 minutes as this carbon is sp3 hybridized. So when it undergoes elimination, this carbon becomes a double bonded carbon, an sp2 hybridized carbon. Here the bond angle is 120 degree. Since the bond angle increases, there is some relief from angular strain or steric strain. That is the reason for why tertiary substrates are more readily undergoing elimination. There are four types of beta eliminations, namely E1, E2, E1CB and EI. E1 is unimolecular elimination, E2 bimolecular elimination, E1CB elimination, unimolecular elimination through conjugate base. EI is intramolecular elimination and it is usually pyrolytic elimination. Beta elimination through E1 elimination mechanism. This E1 mechanism involves two steps. The first step is ionization, removal of nucleophilic leaving group to form a carbocation intermediate. So the first step is the formation of carbocation, and this is the slow step as it involves bond breaking. And this first step is exactly like the first step of SN1 mechanism. And in the second step, there is deprotonation of the carbocation. A proton from beta carbon is eliminated with a base, normally water. So after deprotonation, it results in the formation of an alkene. As I said, the first step involves bond breaking, therefore it is the slow step or the rate determining step, and it involves only the substrate. Therefore the rate equation contains only the concentration of the substrate. Therefore this reaction follows first order kinetics. The second step is removal of an electropile, usually a proton, which we call as deprotonation, and this deprotonation takes place from a carbocation. So for the second step, reactant is carbocation, product is alkene. From a charged particle, a neutral molecule is generated along with the formation of a new pi bond. Since it involves the formation of a new bond and the reaction goes from ion to neutral molecule, this step is the fast step. Here is another example for E1 elimination. dehydration of tertiary butyl alcohol using concentrated sulfuric acid. The moment you add concentrated sulfuric acid with an alcohol, the acid breaks to give a proton, and that proton joins with the oxygen of OH. Oxygen here has got two lone pairs. So one of the lone pairs combines with the proton, and this is what we call as protonation of alcohol. The moment you add acid with alcohol, the alcohol undergoes spontaneous protonation. So this is not considered as a separate step. And now only the reaction starts. We start heating this protonated alcohol. Once we heat this, carbon-oxygen bond breaks and a water molecule is removed, resulting in the formation of a carbocation. So this first step involving bond breaking is the slow step, and the slow step is called rate determining step. And this carbocation undergoes deprotonation in the second step. So the carbocation reacts with the basic component of the acid, the conjugate base of the acid, and this takes up a proton from beta carbon. So once this beta hydrogen is removed as a proton, this carbon will get a minus. That minus will join with the plus to form a new pi bond. So this second step starts with a cation and ends with a neutral olefin. Therefore, this step, the deprotonation step, is a very fast step, and this does not involve in the rate equation, and this is not the rate determining step. So it is the first step, the bond breaking step, the slow step being the rate determining step in this reaction. E1 elimination reactions are regioselective and follow Zaitsev rule. Here I have given an alkyl halide. It is treated with water. It is heated with water. In the first step, the bromine is removed as bromide. The carbon to which bromine is connected is alpha carbon. With respect to alpha carbon, this methyl carbon is beta, this carbon is another beta carbon, and this is another beta carbon. So in the first step, when we heat, the bromine carbon bromine bond breaks and bromide is removed, resulting in the formation of carbocation. That is the first step. In the second step, deprotonation can take place from any one of the beta carbon atoms, either this methyl beta carbon or these two methylene beta carbon atoms. But usually deprotonation takes place from the beta carbon present in the ring. Deprotonation takes place by water from beta carbon here. Therefore, the pi bond is formed as an endocyclic pi bond here. Suppose, let us consider elimination, deprotonation is taking place from methyl carbon, the beta carbon. You will have a double bond here in the product, an exocyclic double bond. The product with the exocyclic double bond has only two alkyl substituents with the double bonded carbon atoms. This is a di-substituted alkene. Whereas here, when the pi bond is endocyclic, this is a tri-substituted alkene. In this double bonded carbon, there are two alkyl groups, and here there is one more alkyl. Therefore, this is more substituted. The more substituted alkenes are normally more stable because of higher hyperconjugation. Therefore, this is the major product, the more stable product. So, in E1 mechanism, there are two steps involved. In the first step, the substrate undergoes ionization, resulting in the formation of carbocation. So, up to this point, this is the intermediate. From starting compound to this intermediate, this is the first step. And this reaction involves, and this is the transition state. The energy gap between the substrate and transition state is called the energy of activation of step 1, EA1. But for the second step, the carbocation is the reactant and the alkene is the product. So, and for this step, the energy of activation is very slow, very less. Therefore, this step takes place at a very fast rate, and this is the energy profile of E1 reaction. Factors influencing the rate of E1 reaction. In E1 elimination reaction, there are two steps involved. It follows two-step mechanism. The first step is the rate determining step. If you accelerate the first step, then the overall reaction rate will increase. So for improving the rate of the first step, the leaving group should be a better leaving group. Another factor that influences the rate of the first step is the number of alkyl groups connected to the alpha carbon, the carbon bearing the nucleophilic leaving group. If there are more number of alkyl groups connected to the carbon bearing the leaving group, it undergoes ionization at a very fast rate. The reason is, if it undergoes ionization, it results in the formation of a tertiary carbocation, which is stabilized by inductive effect and more number of hyperconjugations. Therefore, as the number of alkyl groups connected to alpha carbon increases, the rate of E1 reaction increases. As the leaving ability of the leaving group increases, the rate of E1 reaction increases. And next to that, if strong bases like OH minus or RO minus are used, of course they are more favorable for E2 elimination and not for E1. For E1 elimination to operate, we need to have weaker bases like water or alcohol. So usually in E1 elimination reaction, the substrate is heated with water or alcohol like bases and not with strong bases, because the strong bases will lead the reaction by another mechanism, E2 mechanism. For E1 reaction, we have to make use of the weaker bases only, like water or alcohol. Another pathway through which beta elimination is taking place is the E2 mechanism. This E2 elimination reaction follows a concerted mechanism where bond breaking and bond making are taking place simultaneously in a single step. So E2 mechanism is a concerted mechanism. It is a mechanism which takes place in a single step. The most common E2 elimination reactions are dehydrohalogenation of alkyl halides. And this E2 mechanism exhibits second order kinetics because both alkyl halide and the concentration of the base are appearing in the rate equation. Therefore, this E2 mechanism follows second order kinetics. Here is an alkyl halide undergoing elimination, dehydrohalogenation with the help of a base. So the base abstracts the beta hydrogen from here. Once the proton is removed from here, these bonded electrons are moving between these two carbon atoms, and that pushes out the bromide out. So the base hydroxide removes a proton from beta carbon atom, while the halogen leaves from alpha carbon, resulting in the formation of a new pi bond. And this kind of elimination reactions, which are taking place in a single step by a concerted mechanism, are called E2 elimination reactions. This is the energy profile for an E2 reaction. In this reaction, the substrate is approached by the base, leading to a transition state like this, where the carbon hydrogen bond between beta carbon and hydrogen is broken. The hydrogen is gradually removed by the base, and these bonded electrons, as H plus is moving out, these bonded electrons are moving between the two carbon atoms, and that pushes out the bromine as bromide. So this is the transition state. From this, the beta hydrogen and bromine in the alpha carbon are eliminated, resulting in the formation of a new pi bond. So this reaction has comparatively smaller energy of activation when it is compared with the E1 reaction. Therefore, this reaction takes place at a lower temperature than the E1 elimination reaction. E2 reactions are regioselective, and they favor the formation of sites of products. So in this molecule, 2-bromo, 2-methyl butane, the carbon bearing bromine is called alpha carbon, and with respect to alpha carbon, here is a beta carbon, and this is also a beta carbon, and this is one more beta carbon. There are 3 beta carbon atoms, and all the 3 are having hydrogens connected to them. But the hydroxide base removes proton from the more substituted carbon, resulting in the formation of the more substituted alkene as the major product, and this is called sites of product. All E2 elimination reactions are obeying the sites of rule. According to sites of rule, when an alkyl halide has 2 or more different beta carbon atoms, more than one alkene product is formed. In such cases, the major product is the more stable product, that is the one with the more substituted double bond. This is called sites of role, and it is explained with an example here. Here I have given an alkyl iodide, cyclohexyl iodide. Iodine is connected to this carbon. It is called alpha carbon. With respect to this alpha carbon, there are 3 beta carbon atoms, among which 2 beta carbon atoms are symmetrical in similar environment. So I have given the same label for both. Therefore, in this alkyl halide, there are 2 types of beta carbon atoms or beta hydrogens. So when we add a hydroxide, a strong base with this alkyl halide, it removes a proton preferably from beta carbon, because that results in the formation of a double bond which is more substituted. This is the major product. There is a possibility for the formation of one more product by the abstraction of beta hydrogen from beta 1 carbon. But that ends up with an exocyclic double bond. It is a disubstituted alkene, whereas this one is sides of product, the more substituted alkene with an endocyclic double bond. Therefore, according to Zaitsev rule, the more substituted alkene is the major product, and this is the major product. 1-methyl cyclohexene is the major product. The more substituted alkene is more stable, because when there are more number of substituents, more number of alkyl carbon atoms connected, there are more number of allyl hydrogens present. In this case, here is a CH3, here is CH2, CH2 here. Totally 7 allyl hydrogens are here, so it can form 7 hyperconjugation or no bond resonance structure. Whereas in this molecule, this is disubstituted. This is a methylene and this is methylene. So there are 2 allyl carbon atoms present. Both are having 4 hydrogen atoms. CH2 here, CH2 here. Altogether there are 4 hydrogens. Therefore this can form only 4 hyperconjugation or no bond resonance structures. So the one with more number of alkyl substituents is having more number of allyl hydrogens, and hence it has more number of no bond resonance. Since it is having more number of resonance structures, this is more stable. The more stable product is the predominant product. The more substituted alkene is more stable. The more stable product is the major product according to Zaitsev rule. The factors influencing the rate of a E2 reaction. There are 4 important factors which are affecting the rate of a E2 elimination reaction. The first and foremost factor is the strength of the base used in elimination reaction. So the rate of the E2 reaction increases as the strength of the base increases. So usually we make use of hydroxide or alkoxide bases for E2 elimination. Regarding the solvent, polar aprotic solvents increase the rate of E2 elimination. Another important factor is the efficiency of the leaving group, the leaving ability of the leaving group. So better the leaving group, faster will be the E2 reaction. Here I have given various alkyl halides, alkyl iodide, bromide, chloride, fluoride. Among all these, alkyl iodide undergoes elimination at the fastest rate because iodide is the best leaving group among the halides. Another very important factor which influences the rate of E2 reaction is the nature of the substrate which undergoes elimination. If the alkyl halide is a tertiary substrate, the rate of E2 reaction is very high. So this is the order in which elimination reactions are taking place from various alkyl halides. This is the primary alkyl halide, and here it is secondary alkyl halide. This undergoes elimination faster than the primary. The tertiary alkyl halide undergoes E2 elimination faster than the secondary alkyl halide. This is because in the tertiary alkyl halide, the carbon is connected to three alkyl groups which are bulky in size. So there is a higher steric strain existing in this molecule. But when it is attacked by a base, when a base attacks the beta hydrogen, a transition state is formed in which a pi bond is partially formed. Therefore, the carbon is slowly going from sp3 to sp2. From sp3 hybridization to sp2 hybridization. So the substrate has a carbon with the sp3 hybridization, and the product results in carbon-carbon double bond. Double bonded carbon atoms are sp2 hybridized. So when a carbon with a large number of bulky groups goes from sp3 to sp2, the bond angle increases from 109 degrees 28 minutes to 120 degree. So when the bond angle increases, the angular strain decreases. So the extent to which the angular strain or steric strain is removed is highest at tertiary alkyl halide. Therefore, tertiary alkyl halides are undergoing E2 elimination at the fastest rate. It is because the substrate has a sp3 hybridized carbon. When it undergoes elimination, it forms a carbon-carbon double bond. Therefore, it becomes sp2 hybridized. In sp3, it has the bond angle of 109 degrees 28 minutes. But in sp2, it has 120. So the bond angle increases, the bulky groups are going away from each other. That is why the tertiary alkyl substrates undergo E2 elimination at the fastest rate due to highest extent of relief from steric strain. The stereochemistry of E2 elimination reaction. The most important requirement for E2 elimination is the leaving group and the beta hydrogen should be coplanar. This is the most important condition for E2 elimination to operate. The leaving group at the alpha carbon and the hydrogen in the beta carbon should be coplanar. They should be in the same plane, coplanar or periplanar. They can either be syncoplanar or anticoplanar. E2 elimination occurs most often in the anti-periplanar geometry. So the leaving group in the alpha carbon and the hydrogen in the beta carbon should be coplanar or periplanar, and both of them can either be syn or anti-coplanar. And E2 elimination operates faster with anti-periplanar geometry. It is better if the leaving group and beta hydrogen are in the opposite directions. This arrangement allows the molecule to react in the lower energy staggered conformation. And this arrangement allows the incoming base and the leaving group to be away from each other. So the base is abstracting beta hydrogen, but the leaving group is in the opposite side. Therefore, the incoming base, which is abstracting the proton, and the electron-rich leaving group are away from one another. So there is no possibility for any kind of repulsion between the base and the electron-rich leaving group. This is the staggered conformation of an alkyl halide. Here halogen X is connected to alpha carbon, and this is the hydrogen connected to beta carbon. So this is the staggered conformer of alkyl halide, in which the halogen in the alpha carbon, hydrogen in the beta carbon are anti-periplanar or anti-coplanar. Both are on the same plane, but they are in the opposite direction. Both are at an angle of 180 degree. For E2 elimination to take place, a strong base approaches the beta hydrogen. Since it is approaching the beta hydrogen from this side, there is no possibility for any kind of repulsive interaction between this electron-rich base and this electron-rich leaving group. Therefore, the elimination reaction takes place through a lower energy transition state, resulting in the formation of an alkene. So, the anti-periplanar conformation allows the base to abstract the beta hydrogen by being far from the nucleophilic leaving group. This reaction is an example for syn elimination. This is the chlorine connected to alpha carbon, and this is the beta hydrogen, and these two are in the same plane and in the same direction. The dihedral angle between these two is 0 degree. Therefore, the CCl bond and CH bond are coplanar, and they are syn coplanar. So when a beta hydrogen is abstracted by a base, the base has to approach the beta carbon through this way. When it comes through this way, it has to be repelled by the electron rich leaving group. Since both are electron rich, both are repelling each other. Because of this repulsion, the reaction is not taking place at a faster rate. Therefore, the syn elimination is taking place at a slower rate than the elimination in molecules where the groups are anti-coplanar. So E2 eliminations are taking place at a faster rate in anti-periplanar conformations than syn-periplanar conformations. E2 elimination reactions in six-membered rings. To explain this, I have taken the example of chlorocyclohexane. This can exist with two different conformations. One in which chlorine is oriented equatorially. In the other one, chlorine is oriented axially. When a bulky group is oriented axially, it will experience 1,3 diaxial repulsion and hence it is less stable. We know for E2 elimination to operate, the two groups which are eliminated should be with a dihedral angle of either 0 degree or 180 degree. 0 degree means they should be syn-coplanar. 180 degree means they should be anti-periplanar. So when the chlorine is oriented in the equatorial direction, it can neither be syn-coplanar nor be anticoplanar with any of the beta hydrogens. Whereas when chlorine is oriented axially, it is anti-periplanar with the beta hydrogens on both the sides. Therefore, E2 elimination is possible only from this conformation, which is a less stable conformation. Therefore, for elimination, E2 elimination to take place in a cyclohexane system, the two eliminating groups should be oriented diaxially. That means elimination must occur only from the less stable conformer. In chlorocyclohexane, when the chlorine is oriented axially, this is the less stable conformer due to 1,3 diaxial repulsion. When it is oriented axially, it is anticoplanar with both the beta hydrogens. So when we add a base with this, the base abstracts the beta hydrogen. The bonded electrons move here, pushing this chloride out. So in chlorocyclohexane, the less stable conformer where chlorine is oriented in the axial direction, E2 elimination takes place with ease. Here I have given another example, dehydrohalogenation of cis-1-chloro-2-methyl cyclohexane. Here the methyl and chlorine both are alpha bonds, both are downward bonds. In this conformer, chlorine is in the axial direction and it has two beta hydrogens which are anti-periplanar with this chlorine. Whereas it's another conformer I have given, chlorine is oriented in, when this undergoes ring flipping, it generates another conformer where chlorine is oriented in the equatorial direction, methyl is oriented in the axial direction. Here when the leaving group chlorine is oriented equatorially, so when a leaving group is oriented in the equatorial direction, it can neither be syn-coplanar nor be anticoplanar with any of the beta hydrogens. Therefore, elimination from this conformer is ruled out. So it is possible only from this conformer where there are two beta hydrogens available anti-periplanar with respect to this chlorine. Antiperiplanar means the leaving group and the beta hydrogen are at 180-degree dihedral angle. In cis 1-chloro-2-methyl cyclohexane, elimination takes place from the less stable conformer where chlorine is oriented axially. This has two beta hydrogens. So elimination can take place either with this beta hydrogen or this one. If this beta hydrogen is eliminated, it results in the formation of a more substituted alkene. Double bond is present in the carbon that is connected with the methyl group. Therefore, it gives this product. Whereas, if another beta hydrogen, this beta hydrogen is eliminated along with chlorine, then it results in the formation of a new pi bond here. And that gives this product. But this product is having only two alkyl substituents connected to the double bonded carbon atoms. This is a di-substituted alkene, whereas this one is a tri-substituted alkene. With the double bonded carbon atoms, this side we have two carbon atoms, allyl carbons. Here we have only one allyl carbon. So 1 plus 2, totally there are 3 allyl carbon atoms connected to the double bonded carbon atoms. Therefore, this is tri-alkyl substituted, whereas this is dialkyl substituted. So the more substituted alkene is more stable. It is called sites of product, and that is the major product. Now let us move on the dehydrohalogenation of trans 1-chloro-2-methyl cyclohexane. So these are the two conformations of trans 1-chloro-2-methyl cyclohexane. Here both chlorine and methyl are oriented in equatorial direction. One is downward alpha bond, another one is upward beta bond. Therefore, this is the trans conformer. Here, chlorine is the leaving group. It is oriented in the equatorial direction. When the leaving group is oriented in the equatorial direction, there is no beta hydrogen oriented coplanar with this. Therefore, it undergoes ring flipping to make the chlorine oriented in the axial direction. Of course, this is the less stable conformer because the two bulky groups are oriented in the axial directions. Both will experience 1,3 diaxial repulsion, but anyhow, E2 elimination is possible only from this conformation. And in this conformer, there is only one beta hydrogen in this side available for E2 elimination. It is anti-periplanar with this chlorine. Therefore, this reaction will result in the formation of only one product in which the double bond is oriented here. Therefore, in trans 1-chloro-2-methyl cyclohexane, elimination is possible only from the axial conformer, and this has only one beta hydrogen available for elimination with chlorine. When we add a base like alkoxide or hydroxide, the base approaches this hydrogen, abstracts it. When the hydrogen is abstracted, these bonded electrons move here, pushing out chloride. That results in the formation of a olefinic double bond here. and this is represented with the hexagonal structure like this. Therefore, here there is no possibility for the formation of a double bond here to make it more substituted. So there is only one product possible, and that has only a double bond, that is di-substituted. Only the less substituted alkene is the only product of this reaction. So in conclusion, for E2 elimination reactions to take place, there should be diaxial arrangement of the leaving group and the beta hydrogen. So the leaving group and the beta hydrogen should be compulsorily diaxial. If the leaving group is oriented in equatorial direction, then the reaction will never go by E2 elimination. It will undergo elimination by some other pathways like E1 reaction. I have given two stereoisomers which are undergoing elimination here. So I have given the elimination reactions of two stereoisomers with the base tertiary butoxide, and these two stereoisomers undergo elimination with the same base in two different ways to give two different products. This is one stereoisomer where three substituents are oriented in the same direction in the beta side. This can be represented with the chair form like this. Always when a problem is given with this hexagonal structure, we should convert it into chair form. This is very important point you should remember. Whenever a problem is given with the hexagonal structure, you should convert it into chair form. Only then you should predict the product. So this stereoisomer with all the three bonds in the beta side, I have converted into chair form. Here the tertiary butyl group, the bulkiest group, it should always, whenever there is tertiary butyl group, the bulky group present in cyclohexane, it should be always oriented in equatorial direction. So in equatorial direction it is in the beta side. Therefore the other two bonds, they are also in the beta side. They also should be represented with upward bonds. So the COOH is in equatorial position, that is also upward, and the bromine is also upward. So now the requirement for E2 elimination is the leaving group should be oriented in axial direction. When it is oriented in axial direction, it has two beta hydrogens, one here, another here. But elimination takes place from this beta hydrogen, resulting in the formation of a new double bond here. So this can be represented with a hexagonal structure like this. So I have given another stereoisomer where two groups are oriented in the beta side. The other one is oriented in the alpha side at the back side. First of all, we have to convert it into chair form. The tertiary butyl bulky group is oriented in the equatorial direction. So in the 1,3 trans, that should be in the equatorial axial. 1,3 position, 1, This is 3. Two groups in 1,3 position to be oriented trans to each other. One should be equatorial, the other should be axial. And these two are 1,4. 1,4 same side cis. That means if this is equatorial, this should be axial. In 1,4 position, cis means equatorial axial or axial equatorial. Tertiary butyl can always be only in equatorial. Therefore, bromine should go to the axial site. Now when we add tertiary butoxide, there is a beta hydrogen available in this carbon, beta carbon. And in this beta carbon there is no hydrogen here, but a different type of reaction is taking place. Tertiary butoxide, instead of abstracting a beta hydrogen from here, it behaves as a base and takes up the most acidic hydrogen of carboxyl group, generating a carboxylate anion. This carboxylate anion undergoes elimination. The minus is shifted here to make a double bond. When a new bond comes here, this bond goes in between these two carbon atoms, pushing the bromine out. So therefore, there is a decarboxylation and dehalogenation is taking place. This bromine and the carboxyl group both are eliminated to make a double bond here. That product we can represent like this. Therefore, these two molecules are stereoisomers. When they are treated with the tertiary butoxide base, both are leading to the formation of entirely different products. Here is a very important problem to explain the mechanism of E2 elimination. Here are two stereoisomers given, methyl chloride and neomethyl chloride. So whenever we are given a problem with the hexagonal structure of cyclohexane, we should convert it into chair form. So in methyl chloride, a methyl group and chlorine in 1,3 positions are cis with respect to each other, and the isopropyl group is trans with respect to each other. Here I have given the chair form of this molecule. So this chlorine and methyl group in 1,3 positions are in the same direction, downward. Methyl is downward, chlorine is downward. With respect to chlorine, the isopropyl is trans. So for isopropyl to be trans with respect to chlorine, this should be oriented in equatorial. 1, 2 di-equatorial is trans. Therefore chlorine and isopropyl both should be equatorial. So this is the chair form of this molecule. But in this, the leaving group is not oriented in the axial direction. As we know, always for E2 elimination to take place, the eliminating group, the leaving group, should be oriented in axial direction. So this molecule should undergo ring flipping to form the less stable conformer, and elimination takes place only from this less stable conformer. So when we add a strong base, the strong base abstracts this beta hydrogen. With respect to chlorine, there is only one beta hydrogen available. Therefore, that is abstracted by base, and this bond is shifted here, pushing this chloride out. So we get a double bond here. So this elimination has only chlorine and hydrogen. We have only one pair which are anti-periplanar. There is no other beta hydrogen with respect to chlorine available. Only one hydrogen, beta hydrogen is available. Therefore, elimination takes place here, resulting in the formation of a olefinic double bond that is represented like this. So this is the elimination product of methyl chloride. Whereas if we take neomethyl chloride, the methyl is in one direction, chlorine and isopropyl are trans with respect to methyl. So if you represent methyl in the equatorial position, or we have to, first of all, we have to take the biggest substituent in the equatorial position. Therefore, we have taken isopropyl in the equatorial position. With respect to this isopropyl, methyl is trans. These two are in 1,4 position. For two groups to be in trans in 1,4 position, they should either be diaxial or be di-equatorial. So isopropyl is already oriented in equatorial direction. Therefore, methyl also should be in the equatorial direction. And with respect to isopropyl, this chlorine is cis. Cis with respect to the isopropyl. If it has to be in 1,2 position, for two groups to be cis, they have to be axial equatorial or equatorial axial. So isopropyl is already in the equatorial side. Therefore, chlorine should go to the axial side. So this is how neomethyl chloride, the hexagonal cyclohexane structure, is converted to chair form. So as I said earlier, you convert the cyclohexane hexagonal structure to the corresponding chair form, and then flip the ring in such a way eliminating group O is oriented in the axial direction. It is already there in the axial direction. Now straight away add base. There are two beta hydrogens available for this chlorine to undergo elimination. Two beta hydrogens are available. Therefore, elimination can take place with this hydrogen to make a double bond here, which will be a disubstituted alkene, or elimination can take place with this hydrogen to make a double bond here, and that will be a trisubstituted alkene. Therefore, the elimination takes place by abstracting this hydrogen. So hydrogen that is present in the more substituted carbon is removed by the base. So the base removes this hydrogen which is present in the more substituted carbon. If this proton, hydrogen is removed as a proton, the bonded electrons will move here to push the chloride out, and we get a double bond here. This is converted to the hexagonal structure, and this has 1, 2, 3. 3 carbon groups, 3 allyl carbon atoms connected to the olefinic double bonded carbon atoms. Therefore, this is a trisubstituted alkene, and this is the almost the only product from neomethyl chloride. So methyl chloride forms the less substituted product, the disubstituted, but neomethyl chloride forms the more substituted alkene. So this problem is a very important problem for examination also. So you can practice this problem several times. Another mechanism by which beta elimination is taking place is unimolecular elimination through conjugate base E1CB. E1 for unimolecular elimination, CB for conjugate base. This E1CB mechanism operates in compounds bearing a poor leaving group. This H should be a poor leaving group. When it is removed from this, it should be very less stable. So the molecule, a compound which is bearing a poor leaving group and an acidic beta hydrogen undergoes elimination by E1CB mechanism. This mechanism is extremely opposite. It is the other pole of E1 elimination. In E1 elimination, intermediate was carbocation, whereas E1CB mechanism has carbanion intermediate. So this molecule has got an acidic hydrogen. For the beta hydrogen to be acidic, the beta hydrogen should hold an electron withdrawing group which can stabilize this carbanion. Therefore, for E1CB elimination to take place, there should be a poor leaving group and there should be an acidic beta hydrogen. For beta hydrogen to be acidic, there should be an electron withdrawing group connected to beta carbon. So this carbanion is the intermediate, and from this carbanion the leaving group is expelled out, resulting in the formation of a olefinic double bond. Therefore, X from alpha carbon, hydrogen from beta carbon are eliminated. Therefore, this is alpha comma beta elimination or beta elimination taking place through a conjugate base intermediate. From this intermediate, leaving group, nucleophilic leaving group is pushed out to get an alkene as the product. As we discussed, E1CB mechanism involves two steps. The first step is the fast step, that is an irreversible deprotonation, removal of beta hydrogen as H plus by a very strong base. That is the first step, and that is the fast step. And the second step is elimination of an anionic leaving group. So here I have explained it with an example. So here is a molecule having a methoxy leaving group. Methoxide anion is a poor leaving group. With respect to this methoxy group, here is the beta hydrogen. So here also there is beta hydrogen, but we prefer this hydrogen because this beta carbon is connected to electron withdrawing nitro group. So when we add a strong base, it removes this beta hydrogen at a fast rate, resulting in the formation of a stable carbanion. Why I am saying stable? Because this minus charge is connected to a minus R group, nitro group. Therefore, this carbanion the conjugate base of this molecule is stable. So this carbanion is stable and the methoxy group is a poor leaving group. Therefore, the elimination of the methoxy group is not taking place at a fast rate. Instead, it is taking place at a very slow rate. Hence, this is the rate determining step which involves only the substrate, the carbanion. So, the overall rate of the reaction depends upon the concentration of the carbanion alone. So, there is only one concentration term of the carbanion involved in rate equation. Therefore, this is an unimolecular elimination. But it is taking place through the conjugate base of the substrate. Therefore, this is called E1CB. The minus carbanion is making a bond here, pushing the methoxide out and it makes a double bond here. So this is one good example for E1CB mechanism. How do we confirm that the abstraction of hydrogen is in the first step? When we replace this hydrogen by deuterium, there is no change in the rate of the reaction. There is no primary kinetic isotope effect observed with this hydrogen. That means when you are replacing the lighter isotope by heavier isotope, the reaction rate should decrease. But there is no change. It shows that the removal of hydrogen is not the rate determining step. And here, when we replace the methoxy group by a better leaving group, then the reaction goes faster. This shows the strong influence of the identity of the leaving group. So, when we change the leaving group, the rate of the reaction changes. Therefore, this second step where the anionic leaving group is removed is the rate determining step. For E1CB mechanism to operate, the beta hydrogen should be acidic, for which there should be, this is the beta hydrogen, this hydrogen should be acidic. To make this hydrogen acidic, there should be some electron withdrawing group present in the beta carbon. The electron withdrawing groups like carbonyl group in aldehyde ketone ester, or a nitro group, or an electron deficient aromatic group may be present at the beta carbon to stabilize the carbanion intermediate. The most common example for E1CB mechanism is dehydration of aldol. This is an aldol. Beta hydroxy carbonyl compounds are called aldol compounds. So this is an aldol. This, on treatment with a base, the acidic hydrogen is removed. The resulting carbanion is stabilized by the electron withdrawing group, the carbonyl group, the minus R group connected to the beta carbon. So this is stabilized by resonance with the enolate. Therefore, the first step in this E1CB is deprotonation. For the deprotonation to take place at a faster rate, there should be an electron withdrawing group connected to the beta carbon. So this dehydration of aldol I have shown here. This is a beta hydroxy carbonyl. The base abstracts a proton from beta carbon with respect to carbon bearing OH. So here the alpha carbon we consider the carbon to which the leaving group is connected, we consider as alpha carbon. The next carbon is beta. So from this beta carbon, the H plus is removed, deprotonation has taken place, resulting in a stable intermediate, resonance stabilized intermediate. So an enolizable carbanion is generated, it is in resonance with enolate. So the carbanion, the conjugate base is resonance stabilized and stable. And in the slow step, the minus charge carbanion is pushing this anionic leaving group out to generate the double bond. So this is the dehydration of an aldol, a good example for E1CB elimination. Another example for dehydration of aldol is given here. This is a beta hydroxycarbonyl, an aldol. See here, this is the carbonyl group. This is alpha carbon with respect to carbonyl, and this is beta. So this is beta hydroxycarbonyl, an aldol compound. When this is treated with a strong base like methoxide, sodium methoxide, first of all, deprotonation from this hydrogen. Now we consider in this E1CB elimination, we consider the carbon to which OH is connected as alpha, this carbon as beta. So usually when you are given a carbonyl compound, we consider the carbon next to the carbonyl as alpha and this as beta. But here in E1CB mechanism, to explain the reaction mechanism, we consider the carbon to which the leaving group, nucleophilic leaving group is connected as alpha carbon, the next carbon is beta. So from beta carbon, the base removes a proton. So deprotonation takes place very readily because the resulting product is an enolizable carbanion, a resonance stabilized carbanion. So here the enolate form is given. So from this enolate, the hydroxide is pushed out. And this is a slow step. Since this is a stable anion, this is not undergoing elimination at a very fast rate. So the hydroxide is eliminated at a slower rate. Therefore, this step, the second step is the rate determining step, and it results in the formation of an alpha beta unsaturated carbonyl compound. So here we have in the carbon, in the beta carbon, there is an electron withdrawing group carbonyl, and the leaving group OH is a poor leaving group. So for E1CB mechanism to operate, the nucleophilic leaving group should be a poor leaving group, and the beta carbon should have been connected to an electron withdrawing group. So these are the conditions in favor of E1CB. So these aldol molecules are fulfilling these conditions. Therefore, the dehydration of these molecules, aldols, is a very good example for E1CB reaction. The E1, E2, E1CB spectrum. So far we discussed three types of beta eliminations. In each case, there is a nucleophilic leaving group which comes off with a pair of electrons, and another electrophilic group, usually H plus, comes off without electrons. So the only difference between these three mechanisms is the order in which these two steps are taking place: the removal of leaving group and removal of the proton. The order in which these two processes are taking place, in that only these three mechanisms are differing. Therefore, there is a spectrum of mechanisms ranging from one extreme in which the nucleofuge or nucleophilic leaving group is eliminated first, very well before the removal of proton, that we call as E1 mechanism. Nucleophilic leaving group is removed first here, and the E1CB is in the another extreme of the spectrum, where the proton is removed first, resulting in the generation of conjugate base. So these are the two extremes, and the E2 reaction involves the simultaneous removal of nucleophilic leaving group and the electrophilic leaving group, usually the proton. But the removal of nucleophilic and electrophilic leaving groups are not exactly simultaneous. That means the E2 mechanism is not lying exactly at the center of the spectrum between E1 and E1CB. So E1 is one end of the spectrum, E1CB is the opposite end of the spectrum, and E2 should be somewhere in the middle. In E1, nucleophilic leaving group is eliminated first, generating carbocation intermediate. In E1CB, deprotonation takes place first, resulting in the formation of carbanion intermediate. In E2, see both the groups, nucleophilic and electrophilic groups, are eliminated simultaneously, but in some cases both are not exactly simultaneous. The pure E2 elimination should be exactly at the middle of the spectrum. E1 at one end, E1CB at the other end. E2 should be exactly at the middle, since nucleophilic and electrophilic leaving groups are simultaneously removed. So the pure E2 elimination should be somewhere in the middle of the E1, E2, E1CB spectrum. However, most of the E2 reactions are not exactly in the middle, but somewhere to one side or the other. For example, the nucleofuge, nucleophilic leaving group may depart little before the proton. This case may be described as an E2 reaction with a small amount of E1 character. In another case, proton may be eliminated little faster than the nucleophilic leaving group, and that is considered as a E2 reaction with a small amount of E1CB character. So this concept can be expressed by a question. In the transition state, which bond, either the beta carbon hydrogen bond or alpha carbon nucleophile bond, which bond is undergoing more cleavage? If CH bond undergoes faster cleavage, that E2 reaction is closer to E1 end. If CH bond is broken faster than CX, then that E2 reaction lies little closer to E1CB end. So which bond undergoes faster cleavage? That decides where the E2 is located in E1, E2, E1CB spectrum. Finally, we are going to discuss the last type of beta elimination reaction. This is called intramolecular elimination, and this is a pyrolytic elimination. The term pyrolytic elimination means an elimination reaction taking place in an organic molecule by the application of heat. Pyre is a Greek word which means fire. That means by the application of heat, we are conducting the elimination reactions. So there are three important pyrolytic eliminations we are going to discuss. The first one is Cope elimination. Here we start with an amine. This amine is oxidized with per acids like metachloroperbenzoic acid or peroxides. So the amine undergoes oxidation to form an amine oxide, an N oxide. So here the nitrogen with the positive charge is going to be removed with these bonded electrons. Therefore, this is the nucleophilic leaving group. So the one that goes out with the bonded electrons. So the carbon to which nitrogen is connected is called alpha carbon. The next carbon is beta carbon, and this is beta hydrogen. So this amine oxide or N oxide, when we heat, the oxide removes a proton from here. The bonded electrons move here, pushing out these bonded electrons with nitrogen. So nitrogen takes up both the bonded electrons. This O minus takes a proton, and that is how a hydroxylamine is generated. Along with that, a double bond is formed here. From alpha carbon, nitrogen is removed. From beta carbon, hydrogen is removed, resulting in the formation of a new pi bond. An alkene is generated. So usually for Cope elimination, we employ the temperature between 80 and 160 degree centigrade. The reaction mechanism of EI elimination involves an intramolecular 5-membered cyclic transition state which is leading to syn elimination product through EI pathway. So here you can see this is amine. This on treatment with a peroxide, it is converted to N oxide, amine oxide. This oxygen, let us consider 1, 2, this is 3, 4 and nitrogen 5. So when oxygen attracts the hydrogen, beta hydrogen here, it makes a weak bond. Therefore, it forms a cyclic, 5-membered cyclic transition state. O minus abstracts the beta hydrogen gradually, and these electrons are moving here, and these electrons are moving to nitrogen. So the reaction is taking place in a single step where hydrogen and nitrogen are removed simultaneously from alpha and beta carbon atoms through a cyclic transition state. And in the cyclic transition state, these two groups are on the same side of the carbon-carbon bond. Therefore, this is called syn elimination. And this looks exactly like Hoffman elimination, where quaternary ammonium salts are treated with base for forming Hoffman products, less substituted alkenes, which we call as Hoffman products. So this reaction also looks like Hoffman elimination, but the base is not applied externally. The base is the O minus that is present in the molecule itself. So the base is part of the leaving group itself. So the base is this O minus. It is present in the leaving group itself. So cope elimination is conversion of an amine to amine oxide and N oxide. This on heating generates an alkene and hydroxylamine. Here one more example I have given for cope elimination. Without this oxygen it had been a tertiary amine, and that on treatment with peracids or peroxide it has formed an N oxide, and this N oxide O minus is the base, and this is alpha carbon and this is beta carbon. So from this beta carbon O minus removes a proton, and this nitrogen takes up the bonded electrons, resulting in the formation of a olefinic double bond. This is another good example for cope elimination. So as I said, cope elimination is very important for examination. This is another very important reaction for examinations, Chugave elimination. This is pyrolytic dehydration of alcohols, pyrolytic elimination of water, or pyrolytic dehydration of alcohols to produce alkenes. And this Chugave elimination involves an intermediate xanthate. Alcohol is converted to a xanthate, and this xanthate on heating undergoes EI elimination, intramolecular elimination, resulting in the formation of an alkene. We shall discuss the mechanism of this reaction in detail. Chugave elimination involves two steps. In the first step, the alcohol is converted to its corresponding alkoxide by treatment with a base, and this alkoxide is then treated with carbon disulfide. O minus attacks at carbonyl, this carbon connected to sulfur by double bond. So when a new bond is made here, one of the pi bonds present here breaks to give S minus. So O connected to this carbon, and that is having S minus, and that is existing as an ion pair with the metal ion. And this salt is then treated with an alkyl halide like methyl iodide. And here SN2 reaction takes place. S minus is the nucleophile, iodide is the leaving group. So S minus attacks the carbon, pushing this iodide out by SN2 mechanism. Therefore, the sulfur gets methylated, and this is what we call as methyl xanthate. The resulting methyl xanthate, this is the methyl xanthate, and here this is the leaving group. This oxygen is the leaving group. The carbon to which it is connected is alpha carbon, and this is beta carbon. So this is the methyl xanthate we have obtained from the first step. When it is heated to a temperature about 200 degrees centigrade, 120 degree to 200 degrees centigrade, when we heat, an alkene is generated through an intramolecular elimination. This reaction goes through a 6-membered cyclic transition state. Here you can see sulfur is attracting this beta hydrogen. So slowly these pi electrons are moving towards hydrogen. As a new bond is made here, these electrons are moving here, and these electrons are moving, so simultaneous processes are taking place. Therefore, there is a weak bond. When these electrons are moving towards hydrogen, a weak bond is formed in the transition state. And this is a six-membered transition state. From that, on further heating, the sulfur takes up this hydrogen completely, pushing this bond here. So a double bond is generated. Once a new bond is formed here, this bond is taken up by oxygen. That is how we end up with an alkene here, along with another product which decomposes to carbonyl sulfide and methane thiol. The third very important intramolecular elimination, a pyrolytic elimination, is ester pyrolysis. An ester containing a beta hydrogen atom on vacuum pyrolysis decomposes to give a carboxylic acid and an alkene, or the ester containing beta hydrogen undergoes elimination to give an alkene. So here is an example for pyrolysis of ester. Ethyl acrylate. So this is acrylic acid and this is the ethyl ester of acrylic acid. This oxygen is connected to an alkyl group. For this alkyl group, this oxygen is going to be a nucleophilic leaving group. Therefore, this carbon is called alpha carbon. The next carbon is labeled as beta carbon. So, this kind of esters with beta hydrogen, when heated to temperature around 600 degrees centigrade, they undergo elimination to generate an acid and an alkene. The mechanism we shall discuss. This is ethyl acrylate. This is the ethyl group and this is ethyl acrylate. This on heating, you can see the carbonyl pi bond slowly breaks and moves towards this beta hydrogen. So this is the carbon to which the leaving group, nucleophilic leaving group oxygen is connected. Therefore this is alpha and this is beta. So the pi electrons of the carbonyl group are gradually moving towards hydrogen. As these electrons are moving towards hydrogen, this bond breaks and the electrons are moving here. As these electrons are coming here, these electrons are moving in between this carbon and oxygen, and this is shown in the transition state. So the pi bond is moving between oxygen and hydrogen, and this sigma bond moves here to make a pi bond, and this sigma bond moves here to make another pi bond, and that results in acrylic acid and an alkene. Here earlier we had a carbon-carbon single bond. Now one more bond is made here. So this has become an alkene. So this is also a 1,2 or alpha, beta or beta elimination. This is a 1,2 elimination. Ester pyrolysis is possible in 1,3 or 1n fashion also. Here I have given an example for ester pyrolysis where 1,3 elimination is taking place. So here the ester group is connected here. This is alpha carbon, let us say 1. This is 2 and this is 3. So the one we have discussed here is 1,2 elimination. All beta eliminations are 1,2 eliminations. But here this is 1,3 elimination. The carbonyl group is suitably oriented here to abstract the hydrogen in the third carbon as shown with the arrow marks. So this results in the removal of two groups and resulting in the formation of a new bond. So this is also an ester pyrolysis, but it is a 1,3 pyrolytic elimination of an ester. Under EI mechanism, so far we discussed Chugave elimination, Cope elimination and ester pyrolysis. All these pyrolytic eliminations occur most commonly by EI mechanism involving a cyclic transition state. The cyclic transition state may be a 4-membered or 5-membered or 6-membered ring. And all these elimination reactions are taking place in a concerted manner, in a single step. All these elimination reactions are single step reactions. So whatever the mechanism we have discussed for Cope or Chugave or ester pyrolysis, all these are taking place by concerted mechanism as a single step mechanism. And all these are syn elimination. Both the groups which are eliminated from the same side. So evidences for this mechanism are these reactions follow first order kinetics, and so far no reaction intermediate has been isolated. Whatever the cyclic structure we have discussed are only transition states and not the intermediates. Therefore, no intermediate has been isolated so far, which suggests the reactions are undergoing a reaction elimination through concerted mechanism. And in all these reactions, the free radical inhibitors show no effect. That means all these elimination reactions are not going through a free radical mechanism. I have given a long lecture on elimination reactions, alpha elimination, beta elimination. Under beta elimination, we discussed E1, E2, E1CB, EI. I hope you enjoyed all these explanations. Thank you.